What that really means is how much can we zoom into the energy scale of this peak before we start to lose information and get fuzzy. And this doesn't just have to do with the qualities of the crystal. Any crystal will have specific characteristics that make it more or less energy precise, but also if we want to have a high level of energy precision, then we need to also make sure that our electronics, like our photomultiplier tube, is also developed for high energy resolution. That means none of the electronic processes that are happening in there during the amplification mess up the information that we have originally from the crystal about the energy of the incoming particle. And we also have to make sure that our data collection and analysis techniques retain that information as well and don't mess anything up or blur the image in any way. And then we have timing resolution. And similar to energy resolution, this just means how closely can we zoom in on that horizontal time axis and still be able to clearly see what's going on. So imagine this. I want to know if two events happened at the exact same time or if they happened one after the other. But the events themselves were separated by 10 nanoseconds. So in order to determine if they happened at the same time or one after the other, I would need a detector that is capable of seeing nanosecond timescales. If my detector is not that precise in the time regime, then all I will see are two events that are blurred and seem like they are on top of one another. But if my detector is sharp enough, then I can zoom in as far as I need to on the horizontal axis, and I can see that there actually is a few nanoseconds of space between them. And that is why we care about these time and energy resolutions, because if we're doing an experiment in which we need to know that things happen at the exact same time very precisely, or if we need to measure very precisely the energies of particles that we detect, then we want detectors that are able to measure those energies and those times as precisely as possible. And so we will spend a lot of money and spend a lot of time in testing and characterizing these detectors to make sure that we know without a shadow of a doubt that we can trust their energy measurements and their time measurements. And we can actually do measurements to quantify both of these resolutions. So take, for example, the energy resolution. Imagine this. We have this particle that we are detecting coming into our detector over and over, and we want to know the energy of that particle. We know that this particle is always the same and it always carries a specific amount of energy, but we want to know how well our detector can actually measure that energy. So what we do is we develop a data acquisition system which takes in these peaks and measures the height of every peak that it detects, or it measures the energy of the peaks. If the energy resolution of the detector is good, then it will be very good at measuring that height and that energy. And it will give us a reliable energy every time that we measure that particle that is very close to the same amount of energy that is actually in the particle. But if it's bad at measuring the energy and has a bad energy resolution,